Chapter 6 Landforms of 9 Glaciation, the Ice Age, and Types of Ice Masses during the Pleistocene Period, or the Ice Ages, about 30,000 years ago. Great continental ice sheets covered much of the temperate latitudes. It is estimated that more than 12 million square miles of the northern hemisphere were buried by ice, half of which was in North America and the rest in Europe. Greenland and the high mountains of Eurasia, Fig. 46. The warmer climate that followed caused the ice sheets to retreat. Today, only two major ice caps are still present, in Greenland and Antarctica. The former covers an area of 720 square miles, while the latter is more than 3 million square miles. They are made up of compact sheets of ice, hardened and crystallized to a depth of over a mile. In Marie-Bayard Land, Antarctica, the ice cap was measured and found to be more than 14 feet thick. Under such a colossal weight, the land sinks gradually. From the central dome of the ice cap, the ice creeps out in all directions to escape as glaciers. The peaks of the loftier mountains project above the surface as nunataks. When the ice sheets reach right down to the sea, they often extend outwards into the polar waters and float as ice shelves. They terminate in precipitous cliffs. When they break into individual blocks, these are called icebergs. While afloat in the sea, icebergs assume a tabular or irregular shape, and only 1/9 of the mass is visible above the Fig. 46, the extent of continental ice sheets in the Ice Age's surface. They diminish in size when approaching warmer waters and are eventually melted, dropping the rock debris that was frozen inside them on the seabed. Apart from Greenland and Antarctica, glaciation is still evident on the highlands of many parts of the world, which lie above the snow line. This varies from sea level in the polar regions to 4,000 feet in the Alps and 17 feet at the equator, as on my Kilimanjaro. Permanent snow fields are sustained by heavy winter snowfall and ineffective summer melting and evaporation. Where the slopes are gentle and the hollows are sheltered from both direct sunlight and strong winds, any snow that falls is rapidly accumulated. Part of the surface snow may melt during the day, but by nightfall it is refrozen. This process is repeated until it forms a hard, granular substance known as neve in French or tint in German. Owing to gravitational forces, the neve of the upland snowfield is drawn towards the valley below. This is the beginning of the flow of the glacier, river-rot ice. It normally assumes a tongue shape, broadest at the source but becoming narrower downhill. Though the glacier is not a liquid, under the continual pressure from the accumulated snow above, it moves. The rate of movement is greatest in the middle W. Here there is little obstruction. The sides and the bottom are maximum extent of the ice sheet's Fig. 47, the different rate of glacial movement. A glacier moves faster in the center than the sides held back by friction with the valley side spurs and the valley floor. If a row of stakes is planted across a glacier in a straight line, they will eventually take a curved shape down the valley, showing that the glacier moves faster at the center than the sides. Fig. 47. In the Alps, the average rate of flow is about 3 feet a day. In Greenland, it may be more than 50 feet, but in Antarctica, where there is little heat to melt the ice, glaciers move only a few inches a day. The Lech Glacier in the Bernese Oberland of Switzerland is 10 miles long, affording some spectacular sights to alpine tourists. Though it is the longest glacier in Europe, it is short compared with those of Alaska and the Himalayas, which measure more than 5 times that length. At the foot of mountain ranges, several glaciers may converge to form an extensive ice mass called a Piedmont Glacier. The best-known Piedmont Glacier is the Malaspina Glacier of Alaska, which is 65 miles long and 2 miles wide, covering an area of more than 1.6 square miles. Combined glaciers of such dimensions are now rare, and in most continents only valley or alpine glaciers are seen. Landforms of highland glaciation generally gives rise to erosional features in the highlands and depositional features on the lowlands, though these processes are not mutually exclusive because a glacier plays a combined role of erosion, transportation, and deposition throughout its course. A glacier erodes its valley by two processes: plucking and abrasion. By plucking, the shire freezes the joints and beds of the underlying rock, tears out individual blocks, and drags them away. Abad S0, en Lee Esser cratches, scrapes, polishes 48 downloaded from Shashidthaka 23. Blog, com and scours the valley floor with the debris throw 2n into it. These fragments are powerful tools of denudation. Large angular fragments cut deep into the underlying rocks, so all glaciated floors be evidence of striation or scratching. The finer materials smooth and polish the rock surfaces and produce finely ground rock flour. The rate of erosion is determined by several factors such as the velocity F flow r, gradient of the slope, the weight of the glacier, the temperature of the ice, and the geological structure of the valley. The characteristic features of a glaciated highland are as follows. 1. Corrick, cirque or cum. The downslope movement of a glacier from its snow-covered valley head and the intensive shattering of the upland slopes tend to produce a depression where the jim or neve accumulates. The process of plucking operates on the back wall, steepening it, and the movement of the ice abrades the floor, deepening the depression into a steep horseshoe-shaped basin called a cirque in French. It is also known as a corrie in Scotland and a cum in Wales, Fig. 48. There is a rocky ridge at the exit of the corrie, and, when the ice eventually melts, water collects behind this barrier to form a corrie lake or tarn. Fig. 48. Development of a corrie arêtes and pyramidal peaks. When two corries cut back on opposite sides of a mountain, knife-edged RTDGs are formed called arêtes, a French word. A now en British example of an arête is the Striding G on Helvellyn in Westmoreland, where three or more CLR9 use cull act together, their ultimate recession will form an angular earn or pyramidal peak. The Matterhorn of Switzerland is a classic example, Fig. 49, 3 Bergschrund, at the head Otter Glacier, where it begins to leave the snow-tealed Otter Corrie. A deep vertical crack opens up called a Bergschrund in German or Rimme in French. This happens in summer when, although the ice continues to move out of the corrie, there is no new snow to replace it. In some cases, not one but several such cracks occur. The Bergschrund presents a major obstacle to climbers. Further down, where the glacier negotiates a bend or a precipitous slope, more crevasses or cracks are formed. Fig. 48. A U-shaped valley in Switzerland. The valley sides are steep, but the floor is flat. There is a ribbon lake in the valley bottom Swiss National Tourist Office for U-shaped glacial trough. The glacier on its downward journey, fed by ice from several corries like tributaries that join a river, begins to wear away the sides and floor of the valley down which it moves. It scratches and grinds the bedrock, removing any rock, debris, and surface soil. It tends to straighten any protruding spurs on its course. The interlocking spurs are thus blunted to form G. A valley which has been glaciated takes a characteristic U-shape, with a wide, flat floor and very steep sides. After the disappearance of the ice, deep sections of these long, narrow glacial troughs may be filled with water forming N-Bibon lakes, such as Loch Ness and Lake Ullswater 50 downloaded from Shashidthaka 23, blog, com in Britain. They are sometimes referred to as trough lakes or finger lakes. 5. Hanging valleys. The main valley is eroded much more rapidly than the tributary valleys as it contains a much larger glacier. After the ice has melted, a tributary valley, therefore, hangs above the main /AI so that its stream plunges down as a waterfall. If tributary valleys are termed hanging valleys and may form a natural head of water for generating hydroelectric power. Rock basins and rock steps. A glacier erodes and excavates the bedrock in an irregular manner. Unequal excavation gives rise to many rock basins filled by lakes in the valley trough. Where a tributary valley joins a main valley, the additional weight of ice in the main valley cuts deeper into the valley floor at the point of convergence, forming a rock step. A series of such rock steps may also be formed due to different degrees of resistance to glacial erosion of the bedrocks. 7. Moraines. Moraines are made up of the pieces of rock that are shattered by frost action, embedded in the glaciers, and brought down the valley. Those that fall on the sides of the glacier, mainly screes, form lateral moraines. When two glaciers converge, their inside lateral moraines unite to form a medial moraine. The rock fragments which are dragged along beneath the frozen ice are dropped when the glacier melts and spread across the floor of the valley. Fig. 51. The glacial moraines as ground moraine. The glacier eventually eels on reaching the foot of the valley, and the pile transporting materials left behind at the snout is the terminal moraine or end moraine. Fig. 51. The deposition of the end moraines may be in several succeeding waves, as the ice may melt back by stages so that a scries of recessional moraines are formed. If the glacier flows right down to the sea, it drops its load of moraine in the sea. If sections break of T as icebergs, morainic material will only be dropped when they melt. Fig. 52. Where the lower end of the trough is drowned by the sea, it forms a deep, sleep-sided inlet called a fjord, typical of the Norwegian and South Chilean coasts. Landforms of glaciated lowlands. Landforms of glaciated lowlands are mainly depositional in nature, brought about by both valley glaciers and continental ice sheets. The former leaves behind the eroded materials in only restricted areas. The imprint of ice sheets on the landscape is far more widespread because they advanced through large areas during the ice ages, scouring and removing any surface soil and rock debris on their way. As a result, it has been estimated that almost a third of the total land surface of Europe and North America is littered with glacial and fluvio-glacial materials of all descriptions: moraines, boulder clay, tills, drifts, rock flour, gravels, and sands. Many of them are being re-eroded, resorted and redeposited elsewhere by present-day rivers. Most of the glaciated lowlands have depositional features, but where rock masses project above the level surface, they result in striking features of erosion, such as the Roch Mountainy and Crag and Tail. 1. Roch Mountainy. This is a resistant residual rock hummock. The surface is striated by ice movement. Its upstream side is smoothed by abrasion, and its downstream side is roughened by plucking. 51 of sea movement Crag Dr. Sion C *************************************************************** Fig. 53 Roch Mountainy and is much steeper. The term Roch Mountainy is used to describe such a feature because it resembles a sheepskin wig once worn in France. Fig. 5i. Roches mountainous are found in both highland and lowland glaciated regions. 2. Crag and Tail. The crag is a mass of hard rock with a precipitous slope on the upstream side, which protects the softer leeward slope from being completely worn down by the oncoming ice. It therefore has a gentle tail strewn with the eroded rock debris. The classic example is the Castle Rock of Edinburgh, Scotland. Edinburgh Castle is located on the crag and the High Street on the tail. Fig. 54. The remaining glaciated lowland features are of a depositional nature. Fig. 55. The following are the typical ones: 3. Boulder clay or glacial till. This is an unsorted glacial deposit comprising a range of eroded materials: boulders, angular stones, sticky, clay, and fine rock flour. It is spread out in sheets, not mounds, and forms gently undulating till or drift plains. The landform is rather monotonous and featureless. The degree of fertility of such glacial plains depends very much on the composition of the depositional materials. Some of the boulder clay plains, such as East Anglia and the northern Midwest of USA, form rich arable lands. 4. Erratics. These are boulders of varying sizes were transporting by ice. They came with advancing glaciers or ice sheets, but when they melted, they were left stranded in the region's deposition. They are called erratics because they, composed of materials entirely different from those the region which they are found. Such erratics, thus most useful in tracing the source and direction the ice movement. Sometimes the erratics may be found perched in precarious positions just as the ice dropped them, and they are then termed perch blocks. Examples of such blocks are commonly encountered in both lowland and highland areas in Europe, e.g. Silurian grits are found perched on the Carboniferous limestone of the Pennines. Their presence in large numbers is a hindrance to farming. Fig. 54 Crag and Tail 5. Drumlins. These are swarms of oval, elongated whaleback hummocks composed wholly of boulder clay, with their elongation in the direction of the ice flow that is on the downstream side. They are low hills varying from a few yards to 400 feet in height and may be a mile or two long. They appear a little steeper at the onset side and taper at the leeward end. They are arranged diagonally and so are commonly described as having a basket of eggs topography. Large numbers of them are found in County Down in Northern Ireland and the glaciated plain around the Great Lakes in North America. 6. Eskers. These are long, narrow, sinuous ridges composed of sand and gravel, which mark the former sites of subglacial meltwater streams. They vary from a few feet to 200 feet in height and may be several miles long. In some parts of Maine, USA, the outstanding eskers form a continuous ridge of 100 miles. They are very numerous in Scandinavia, e.g. the Punkaharju esker of Finland. As eskers are made up all highly porous sand and gravel, water is rapidly drained off from their crests, and they may not support many trees, though in Finland they often form tree-covered ridges between lakes. 7. Terminal moraines. These are made up of the drumlin field in northern England. J.K. St. Joseph 52 PV downloaded from Shashidhaka 23 blog. Coarse debris deposited at the edge of the ice sheet to form hummocky and hilly country such as the Baltic heights of the North European plain. Fig. 55. 8. Outwash plains. These are made up of fluvio-sillaceal deposits washed out from the terminal moraines by the streams and channels of the stagnant ice mass. The meltwaters sort and redeposit the material in a variety of forms from the low, hilly heathlands, such as the Lüneburg Heath of the North European plain, to undulating plains, where terraces, alluvial fans, and deltaic deposits of the meltwater streams make up the landscape. Cairns, small rounded hillocks of sand and gravel, may cover part of the plain. Where the deposition takes the form of alternating ridges and depressions, the latter may contain kettle lakes and give rise to characteristic knob army kettle topography. The human aspects of glaciated landforms, though the ice ages were at their height over 30,000 years ago. The effects of glaciation on both landforms and human activities have profound influence in many parts of the world today. Their most striking impact is felt in the temperate regions of Europe and North America, which were once under continental ice sheets. Further south, and on the high mountains all over the world, slow-moving glaciers are still shaping the landscape in the Alps, Andes, Rockies, and Himalayas. Glacial influences on man's economic activities are both favorable and unfavorable, depending on the intensity of glaciation, the relief of the region, and whether the effects of an erosional or depositional nature. In hilly regions such as the mountain slopes of Scandinavia, ice sheets and glaciers have removed most of the topsoil, leaving them quite bare all vegetation. Soils that do exist are so thin that they are incapable of supporting effective agriculture. Glacial drifts in the valleys and benches or Alps, which were not affected by glaciers, have good pastures during summer. Cattle are driven up to graze on the grass and return to the valley bottom in winter. This loy-m of animal migration type of farming is called transhumance. Extensive boulder clay plains, such as those of East Anglia and the Midwest all USA, are some of the most fertile agricultural plains known. The lowest plains of Europe and central USA, with a high proportion of humus, are good farming land too. On the other hand, the sandy or gravelly outwash plains, e.g. the heath-covered Geest of northern Germany, the marshy boulder clay deposits all central Ireland, the barren ice-scoured surlaces of the Canadian and Baltic shields are intertile. The direction of ice movement, plain presence of numerous erratics and perched blocks in parts of Britain and in Alberta. Canada, many of them of gigantic size, obstruct farming and the use of machines. Morainic deposits may dam, or glaciers may hollow out lakes which greatly inconvenience large-scale farming or land development. But when the lakes are eliminated, the old glacial lake beds with their rich alluvium support heavy cropping. Large lakes formed by former glaciation, e.g. the Great Lakes of North America, make excellent waterways. They may also cut deep overflow channels while draining off, making natural rootwaves across a mountainous terrain, e.g. the Hudson-Mohawk Gap, that links the interior with the Atlantic seaboard of USA. On the other hand, in regions where drumlins are dominant, the drainage is either poor or much confused. Terminal and recessional moraines comprise coarse materials all little use to man, but fluvio-glacial deposits are not without their economic significance. In the outwash plains, eskers and kames have been excavated to provide sands and gravels for highway and building construction. The purest sands are extracted to make molds for metal castings. The lake basins of glaciated mountains provide natural reservoirs. In countries like Scandinavia, Switzerland, and Canada, where there is little available coal, streams and waterfalls that plunge down from hanging valleys or other glaciated uplands are being harnessed to provide hydroelectric power. This has helped to develop many of the chemical and metallurgical industries. With the magnificent scene provided by the glaciated mountains, e.g. the French, Italian, and Swiss Alps, large numbers of tourists are attracted to them annually. Skiing, mountain climbing, and sightseeing are all popular with alpine tourists. Chapter 7. Arid or desert. Landforms. Types of deserts. About a fifth of the world's land is made up of deserts, some rocky, others stony, and the rest sandy. Deserts that are absolutely barren and where nothing grows at all are rare, and they are better known as true deserts. If you look at the world map carefully, you will find that there is a certain definite pattern to the location of the world's deserts. You will realize that almost all the deserts are confined within the 15 degrees to 30 degrees parallels of latitude, north and south of the equator. They lie in the trade wind belt on the western parts of the continents, where trade winds are offshore. They are bathed by cold currents, which produce a desiccating effect, so that moisture is not easily condensed into precipitation. Dryness or aridity is the key note. Such deserts are tropical hot deserts or trade wind deserts. They include the Great Sahara Desert, Arabian, Iranian and Thar deserts, Kalahari, Namib, and Atacama deserts, the Great Australian Desert, and the deserts of southwest USA and northern Mexico. In the continental interiors of the mid-latitudes, the deserts such as the Gobi and Turkestan are characterized by extremes of temperatures. The work of winds and water in eroding elevated uplands, transporting the worn-off materials and depositing them elsewhere, has given rise to 5 distinct kinds of desert landscape. 1. Hamada or rocky desert. This consists of larger sandy desert area, in Death Valley, California. U.S. Information Service stretches of bare rocks, swept clear of sand and dust by the wind. The exposed rocks are thorough, smoothed and polished. The region is bare and sterile. The best-known rocky deserts are those of the Sahara Desert, e.g. the Hamada El Homra, Libya, which covers an area of almost 20 square miles. 2. Reg or stony desert. This is composed of extensive sheets of angular pebbles and gravels which the winds are not able to blow off. Such stony deserts are much more accessible than the sandy deserts, and large herds of camels are kept there. In Libya and Egypt, the term Seria is used. Elsewhere in Africa, stony deserts are called Reg 3, or sandy desert. This is a sea of sand which typifies the popular idea of desert scenery. Winds deposit vast stretches of undulating sand dunes in the heart of the deserts. The intricate patterns of ripples on the dune surfaces indicate the direction of the winds. The Calancio sand sea in Libya is characteristic of a sandy desert. In Turkestan, sandy deserts are also known as Kum, 4 badlands. The term badlands was first given to an arid area in South Dakota, USA, where the hills were badly eroded by occasional rainstorms into gullies and ravines. The extent of interaction on hill slopes and rock surfaces was so great that the entire region was abandoned by the inhabitants. Deserts with similar features are now referred to as badlands. E.g. the Painted Desert of Arizona, lies southeast of the Grand Canyon of the Colorado River. 5. Mountain deserts. Some deserts are found on highlands such as plateaus and mountain ranis. Erosion has dissected the desert highlands into harsh serrated outlines of chaotic peaks and craggy ranges. Their steep slopes are cut by wadis, steep-sided, often dry. Valleys, and the action of frost has caned out sharp, irregular edges. In the Sahara Desert, the Ahaga Mountains and the Taibesti Mountains are good examples of desert mountains. The mechanism of arid erosion and landforms are the results of many combined factors, one reacting upon the other. Insufficient rainfall, often less than 5 inches, coming at most irregular penods, coupled with 10 high tempera, 87 degrees F, is the average, and a rapid roll of evaporation are the chief causes of aridity. Subaerial denudation through the processes of weathering, mechanical and chemical, wind action, and the work of water have combined to produce a desert landscape that is varied 56 downloaded from Shashidhaka 23. Blog. Com weathering. This is the most potent factor in reducing rocks to sand in arid regions. Even though the amount of rain that falls in the desert is small, some manage to penetrate into the rocks and sets up chemical reactions in the various minerals. Intense heating during the day and rapid cooling at night by radiation set up stresses in the already weakened rocks so that they eventually crack. As heat penetrates rocks slowly when the outer surface of rocks is being heated by the hot sun, the inner rocks remain quite cool. The heating of the rocks causes the outer surface to expand and so pries itself all tea from the interior rocks so that it peels off in successive, very thin layers. Such an onion-peeling process of mechanical weathering is called exfoliation. Angular rock debris is found in abundance as screes at the foot of upstanding rocks. Similarly, when water gets into the cracks and joints of rocks, and the temperature at night suddenly drops to below freezing point, the water freezes and therefore expands by 10% of its volume. Successive freezing will prise off fragments of rock which accumulate as screes. These rock fragments become the teeth or tools of wind erosion. Action of winds in deserts. The wind, though not the most effective agent of erosion, transportation and deposition, is more efficient in arid than in humid regions. Since there is little vegetation or moisture to bind the loose surface materials, the effects of wind erosion are almost unrestrained. Wind erosion is carried out in the following ways. 1. Deflation. This involves the lifting and blowing away of loose materials from the ground. Such unconsolidated sands and pebbles may be carried in the air or rolled along the ground, depending on the grain size. The finer dust and sands may be removed miles away from their place of origin and be deposited even outside the desert margins. Deflation results in the lowering of the land surface to form large depressions called deflation hollows. The Qattara Depression of the Sahara Desert lies almost 450 feet below sea level. 2. Abrasion. The sand blasting of rock surfaces by winds when they hurl sand particles against them is called abrasion. The impact of such blasting results in rock surfaces being scratched, polished, and worn away. Abrasion is most effective at or near the base of rocks, where the amount of material the wind is able to carry is greatest. This explains why telegraph poles in the deserts are protected by a covering of metal for a foot or two above the ground. A great variety of desert features are produced by abrasion. Scale 3. Attrition. When W-in-borne particles roll against one another in collision, they W-ear each other away so that their sizes are greatly reduced and grains are rounded into millet seed sand. This process is called attrition. Landforms of wind erosion in deserts, in the combined processes of abrasion, deflation and attrition, a wealth of characteristic desert landforms emerge. 1. Rock pedestals or mushroom rocks. The sandblasting effect of winds against any projecting rock masses wears back the softer layers so that an irregular edge is formed on the alternate bands of hard and soft rocks. Grooves and hollows are cut in the rock surfaces, carving them into fantastic and grotesque-looking pillars called rock pedestals, Fig. 56. Such rock pillars will be further eroded near their bases where the friction is greatest. This process of undercutting produces rocks of mushroom shape called mushroom rocks or gur in the Sahara. Fig. 56 rock pedestals or gur 2. Zeugen. These are tabular masses, which have a layer of soft rocks lying beneath a surface layer of more resistant rocks. The sculpting effects of wind abrasion wear them into a weird-looking ridge and furrow landscape. Mechanical weathering initiates their formation by opening up joints at the surface rocks. Wind abrasion further eats into the lying softer layer so that deep lurrows are eloped. The hard rocks then stand above the furrows as ridges or zeugen, Fig. 57, and many even overhang. Such tabular blocks of zeugen may stand 10 to 100 feet above the sunken furrows. Continuous abrasion by wind gradually lowers the zeugen and widens the furrows. Fig. 57 zeugen with horizontal strata of hard and soft rocks. Fig. 58 yardangs with vertical bands of hard and soft rocks. 3. Yardangs. Quite similar to the ridge and furrow landscape of zeugen are the steep-sided yardangs. Instead of lying in horizontal strata upon one another, the hard and soft rocks of yardangs are vertical bands and are aligned in the direction of the pre-ailing winds. Wind abrasion excavates the bands of softer rocks into long, narrow corridors, separating the steep-sided overhanging ridges of hard rocks, called yardangs, Fig. 58. They are commonly found in the Atacama Desert, Chile, but the more spectacular ones with yardangs rising to 25-50 feet are best developed in the interior deserts of Central Asia, where the name originated. 4 mesas and buttes. Mesa is a Spanish word meaning table. It is a flat, table-like land mass with a very resistant horizontal top layer and very steep sides. The hard stratum on the surface resists denudation by both wind and water, and thus protects the underlying layers of rocks from being eroded away. Mesas may be formed in canyon regions, e.g. Arizona, or on fault blocks, e.g. the Table Mountain of Cape Town, South Africa. Continued denudation through the ages may reduce mesas in area so that they become isolated flat-topped hills called buttes. Many of them in arid countries are separated by deep gorges or canyons, Fig. 59. 57 Mesa Fig. 60 round-topped, steep-sided Inselbergs 5. Inselberg. This is a German word meaning island mountain. They are isolated residual hills rising abruptly from the level ground. They are characterized by their very steep slopes and rather rounded tops. They are often composed of granite or gneiss and are probably the relics of an original plateau which has been almost entirely eroded away. Inselbergs are typical of many desert and semi-arid landscapes in old age, c.g. those of northern Nigeria, Western Australia and the Kalahari Desert, Fig. 60. 6 Ventifetes or Drakentor. These arc pebbles faceted by sandblasting. They are shaped and as rock, an Inselberg in the Australian desert Austin thoroughly polished by wind abrasion to shapes resembling Brazil nuts. Rock fragments, mechanically weathered from mountains and upstanding rocks, arc moved by wind and smoothed on the windward side. If wind direction changes, another facet is developed. Such rocks have characteristic flat facets with sharp edges. Amongst the ventifetes, those with 3 wind-faceted surfaces are called Drakentor. These wind-faceted pebbles form the desert pavement, a smooth, mosaic-like region closely covered by the numerous rock fragments and pebbles. 7 Deflation hollows. Winds lower the ground by blowing away the unconsolidated materials, and small depressions may form. Similarly, minor faulting can also initiate depressions, and the eddying action of oncoming winds will wear off the weaker rocks until the water table is reached. Water then seeps out, forming oases or swamps in the deflation hollows or depressions. The Fayum Depression in Egypt lies 130 feet below the sea level. Large areas in the western USA, stripped of their natural vegetation for farming, were completely deflated when strong winds moved materials as dust storms, laying waste crops and creating what is now known as the Great Dust Bowl. In a dust storm, winds may lift dust hundreds of feet high and carry it thousands of miles away. Landforms of wind deposition in deserts, materials eroded and transporting by winds must come to rest somewhere. The finest dust travels enormous distances in the air and may be moved completely out of the desert. It has been estimated that some dust grains travel as far as 2,300 miles before they are finally deposited on land or sea. The dust from the Sahara Desert is sometimes blown across the Mediterranean to fall as blood rains in Italy or on the glaciers of Switzerland. Dust that settles in the Huanghe Basin from the Gobi Desert has accumulated over past centuries to a depth of several hundred feet. As wind-borne materials are sifted according to their coarseness, it can be expected that the coarser sands will be too heavy to be blown out of the desert limits. They remain as dunes or other depositional landforms within the deserts themselves. Since they are rarely static, their migration pattern depends on a number of factors: the size of the particles they carry, the direction and velocity of the winds, the location and nature of the surfaces over which the particles arc transporting, and the presence or absence of water and natural vegetation. The following are some of the major features of wind deposition. 1. Dunes. Dunes are, in fact, hills of sand formed by the accumulation of sand and shaped by the movement of winds. They may be active or L*VC dunes, constantly on the move, or inactive fixed dunes, rooted with vegetation. Dunes are most well represented in the Erg Desert, where a sea of sand is being continuously moved, reshaped, and redeposited into a variety of features. Because of their great contrast in shape, size, and alignment, they have been given a long list of fanciful names, such as attached dune or head dune, tail dune, advanced dune, lateral dune, wake dune, star dune, pyramidal dune, sword dune, parabolic blowout dune, hairpin dune, smoking dune, and transverse dune. However, the following two types of common dunes, Herchat, will be described in more detail. A barken. These are crescentic or moon-shaped dunes which occur individually or in groups. They arc-live dunes which advance steadily before winds that come from a particular prevailing direction. They are most prevalent in the deserts of Turkestan and in the Sahara. Barkans are initiated probably by a chance accumulation of sand at an obstacle, such as a patch of grass or a heap of rocks. They occur transversely to the wind, so that their horns thin out and become lower in the direction of the wind due to the reduced frictional retardation of the winds around the edges. The windward side is convex and gently sloping, while the leeward side, being sheltered, is concave and steep, the slip face. Fig. 61. The crest of the sand dune moves forward as more sand is accumulated by the prevailing wind. The sand is driven up the windward side, and on reaching the crest, slips down the leeward side so that the dune advances. The rate of advancement varies from 25 feet a year for the high dunes measuring up to 100 feet high to 50 feet a year for the lower dunes which may be only a dozen feet high. The migration of the Barkans may be a fiat to desert life, for they may encroach on an oasis burying palm trees or houses. Long-rooted sand-holding trees and grasses are therefore planted to halt the advance of the dunes, thus preventing areas of fertile land from being devastated. Under the action all winds, Barkans take a chaotic changing pattern. Several Barkans may coalesce into a line O. Irregular 59 downloaded from Shashidthaka 23 blog. Ridges, ever-changing with the direction or the winds. Ergs or sandy deserts are thus most difficult to cross. B. Seefs or longitudinal dunes. Seef is an Arabic word meaning sword. They are long, narrow ridges of sand, often over 100 miles long, lying parallel to the direction of the prevailing winds. The high, serrated ridges may attain a height of over 200 feet. The crestline of the Seef rises and falls in alternate peaks and saddles in regular successions, like the teeth of a monstrous saw. The dominant winds blow straight along the corridor between the lines of dunes so that they are swept clear of sand and remain smooth. The eddies that are set up blow towards the sides of the corridor and, having less power, drop the sand to form the dunes. In this manner, the prevailing winds increase the length of the dunes into tapering linear ridges, while the occasional cross winds tend to increase their height and width. Extensive Seef dunes are found in the Sahara Desert, south of the Qattara Depression, the Thar Desert, and the West Australian Desert. Fig. 62. Fig. 62 longitudinal dunes, Seefs 2. Loess. The fine dust blown beyond the desert limits is deposited on neighboring lands as low. It is a yellow, friable material and is usually very fertile. Loess is in fact fine loam, rich in lime, very coherent and extremely porous. Water sinks readily so that the surface is always dry. Stream have cut deep valleys through the thick mantle of so loess and badland topography. May develop FT is soft that roads constructed through a loess are soon sink, and their walls rise steeply. The most extensive deposit of loess is found in northwest China in the Loess Plateau of the Huang-Ho Basin. It is estimated to cover an area of 250,000 square miles, and the deposits have accumulated to a depth of 200 to 500 feet. In China, such yellowish 60 wind-borne dust from the Gobi Desert is called Huangtu, the yellow earth. But the original term loess actually comes from a village in Alsace, France, bearing that name, where such deposits occurred. Similar deposits also occur in some parts of Germany, France, and Belgium, and are locally called Linean. They are also wind-borne, but were blown from material deposited at the edge of ice sheets during The ice ages. In parts of the Midwest, USA loess was derived from the ice sheets which covered northern North America and is termed adobe. Landforms due to water action in deserts, few deserts in the world, are entirely without rain or water. The annual precipitation may be small, 5 to 10 inches, and comes in irregular showers. But thunderstorms do occur, and the rain falls in torrential downpours, producing devastating effects. A single rainstorm may bring several inches of rain within a few hours, drowning people who camp in dry desert streams and flooding mud-baked houses in the oases. As deserts have little vegetation to protect the surface soil, large quantities of rock wastes are transporting in the sudden raging torrents or flash floods. Loose gravels, sand and fine dust are swept down the hillsides. They cut deep gullies and ravines, forming badland topography. Subsequent downpours widen and deepen the gullies when they wash down more soft rocks from the surface. There is so much material in the flash floods that the flow becomes liquid mud. When the masses of debris are deposited at the foot of the hill or the mouth of the valley, an alluvial cone or eon or dry delta is formed, over which the temporary stream discharges through several channels, depositing more material. The pasty alluvial deposits are subjected to rapid evaporation by the hot sun and downward percolation of water into the porous ground, and soon dry up, leaving mounds of debris. Apart from gullies, there are many larger dry sea annels or valleys. These are deepened by vertical corrosion, by raging torrents during the occasional cloudbursts. These other wadis and are dry for most of the time. Some desert streams are fed by the melting snow of the distant mountains outside the deserts, and rivers flow as exotic streams. The water carves out steep walls, which rise abruptly from such gorges are termed chebka. In arid and semi-arid areas, the outflowing streams from the upland regions are both short and intermittent. They drain into the lower depressions, so that drainage is almost entirely internal. Sometimes water collected in a depression or a desert basin does not completely disappear by evaporation or seepage, and a temporary lake is formed. Such lakes contain a high percentage of salts because of high evaporation and are glistening white when they dry up. The lakes and the alluvial plains formed by them are called playas, salinas or salas in the United States and Mexico, and shots in northern Africa, Fig. 63. The floor of the depression is made up of two features, the bahada and the pediment. The bahada is a depositional feature made up of alluvial material laid down by the intermittent streams. The pediment is an erosional plain formed at the base of the surrounding mountain scarp. Chapter 8. Limestone and Chalk. Landform. Limestone and chalk. Limestone and chalk are sedimentary rocks, all organic origin, derived from the accumulation of corals and shells in the sea. In its pure state, limestone is made up of calcite or calcium carbonate, but where magnesium is also present, it is termed dolomite. Chalk is a very pure form of limestone, white and rather soft. Limestone is soluble in rainwater, which, with carbon dioxide from the air, forms a weak acid. A region with a large stretch of limestone, therefore, possesses a very distinct type of topography. It is then termed a karst region, a name derived from the karst district of Yugoslavia, where such topography is particularly well developed. Characteristic features of a karst region. Generally speaking, karst regions have a bleak landscape, occasionally broken by precipitous slopes. There is a general absence of surface drainage, as most of the surface water has gone underground. Streams rising on other rocks only flow over limestone for a short distance and then disappear underground. For the greater part of their course, they cut their way along the joints and fissures, all the rock wearing out a system of underground channels. The surface valleys are therefore dry. When the water penetrates to the base of the limestone and meets non-porous rocks, it re-emerges onto the surface as a spring or resurgence. Limestones are well jointed, and it is through these joints and cracks that rainwater finds its way into the underlying rock. Progressive widening by rainwater charged with carbon dioxide forms a diluter acid Fig. 64. Limestone pavement. A limestone escarpment. Notice that the valley is cultivate HTU. Institute of Geological Science, V. Ultivated, but the limestone is bleak, and trial solution enlarges these cracks into trenches, and a most intriguing feature called limestone pavement is developed. The enlarged joints are called grikes, and the isolated, rectangular blocks are termed dints. The limestone pavements may have been formed beneath the soil and are now exposed by the removal of the soil cover Fig. 64. On the surface of the limestone are numerous swallow holes, which are small depressions carved out by solution where rainwater sinks into the limestone at a point of weakness. They are also known as sink holes. Gaping Gill in Yorkshire is a line example. These holes grow in size through continuous solvent action. Once water has sunk into the limestone, it etches out caverns and passages along joints or bedding planes. When the roof of an underground tunnel collapses, a precipitous limestone gorge such as the Cheddar Gorge is formed. Where a number of swallow holes coalesce, a larger hollow is formed and is called a doline. Fig. 65. Several dolina may merge as a result of subsidence to form a larger depression called a nuvala. Some of them are a mile across, containing much clay soil from the limestones, weathered after their subsidence. In Yugoslavia, some very large depressions called a limestone pavement poljk may be as large as 100 square miles, but these are partly due to faulting. During the rainy season, parts of the floor which are at or near the water table may become temporary lakes, but the dry areas are fertile and may support large illages. Where subterranean streams descend through swallow holes to underground passages, the region may be honeycombed with caves and caverns, some containing ponds and lakes. The most spectacular underground features that adorn the limestone caves are stalactites, stalagmites, and pillars. Stalactites are the sharp, slender, downward-growing pinnacles that hang from the cave roofs. The water carries calcium in solution, and when this lime-charged water evaporates, it leaves behind the solidified crystalline calcium carbonate. As moisture drips from the roof, it trickles down the stalactite and drops to the floor where calcium is deposited to form stalagmites. They are shorter, fatter, and more rounded. Over a long period, the stalactite hanging from the roof is eventually joined to the stalagmite growing from the floor to form a pillar. Fig. 66. Such features are commonly seen in any well-developed limestone caves, e.g. Batu Caves, Kuala Lumpur, Mammoth Caves, Kentucky, and Carlsbad Cave. New Mexico, in USA, and Postojna Caves, Yugoslavia. The major limestone regions of the world, the most characteristic stretch of limestone occurs in northwest Yugoslavia. Other regions include the Courses district of southern France, the Pennines of Britain, Yorkshire and Derbyshire in particular, the Kentucky region of the United States, the Yucatan Peninsula of Mexico, the Cockpit country of Jamaica, and the limestone hills of Perlis. Human activities of karst regions are often barren and at best carry a THM layer of soil. The porosity of the rocks and the absence of surface drainage make vegetative growth. Fig. 66. Limestone Cave Dry Valley. A dry valley in the chalk region of southern England difficult, so that limestone can usually support only poor grass and short turf. Some sheep grazing is possible. Limestone vegetation in tropical regions, however, is luxuriant because of the heavy rainfall all the year round. Settlements are scattered, and the population is old and sparse. The only mineral of importance is lead, which occurs in veins in association with limestone. Besides this, good quality limestones are often used as building materials or quarried for the cement industry. In West Malaysia, the limestone outcrops of the Kledang Range and the Main Range are quarried for the Pan-Malaysian and Tasik cement works. Stalactites, calcite pillar stalagmites, underground cavern formed by solution in a zone of weakness stream flowing through underground passages. 64. Chalk. The landforms of chalk are rather different from those of other limestones. There is little or no surface drainage, and valleys which once contained rivers are now dry. These are often called coombes. The chalk forms low rounded hills in southern and southeastern England, where they are called downs, and in northern France. The chalk is covered with short turf and in places with woodland, and is used for pasture and sometimes for arable farming. Because of the friable nature of the rock, swallow holes and underground cave networks do not generally develop. Chapter 9. Lakes. General lakes are amongst the most varied features of Earth's surface. They occupy the hollow's OE surface in which water accumulates, tremendously in size, shape, depth, and Mo formation. The tiny ones are no bigger than ponds or pools, but the large ones are so extensive that they merit the name of seas. E.g., the Caspian Sea wick is 760 miles long, as much as 3,215 feet deep, with a total area of 143.550 square miles, and is bigger than the whole of Malaysia. Lakes may exist temporarily filling up the small depressions of undulating ground after a heavy shower, but those which are deep and carry more water than could ever be evaporated remain permanent. Most of the lakes in the world are freshwater lakes fed by rivers and with outflowing streams, e.g., Lake Geneva, Lake Poyang, and the Great Lakes of North America. In regions of low precipitation and intense evaporation, where there are few rivers strong enough to reach the sea, streams drain into a lake, forming a basin of inland drainage. Because of the intense evaporation, these lakes are saline. For example, the Dead Sea has a salinity, salt content, of 250 parts per thousand, and the Great Salt Lake of Utah, USA, has a salinity of 220 parts per thousand. But the Black Sea, into which drain many large rivers, has a salinity of less than 17 parts per thousand. Playas, or salt lakes, are a common feature of deserts. It must be pointed out that lakes are only temporary features of the Earth's crust. They will eventually be eliminated by the double process of draining and silting up. In regions of unreliable rainfall, lakes dry up completely during the dry season. In the hot deserts, lakes disappear altogether by the combined processes of evaporation, percolation, and outflow. Though the process of lake elimination may not be completed within our span of life, it takes place relatively quickly in terms of geological time. The formation and origin of lakes. The following are the various ways in which lakes can be formed. Each of them is placed in a specific category, though in a few cases the lakes could have been formed by more than one single factor. 1. Lakes formed by earth movement, tectonic lakes. Due to the warping, sagging, bending, and fracturing of the Earth's crust, tectonic depressions occur. Such depressions give rise to lakes of immense sizes and depths. They include Lake Titicaca, occupying a huge depression in the Intermont Plateau of the Andes, 12,500 feet above sea level, the highest lake in the world, and the Caspian Sea, 143. 550 square miles, the largest lake, almost 5 times larger than its nearest rival, Lake Superior. B. Rift Valley lakes. Due to faulting, a rift valley is formed by the sinking of land between two parallel faults, deep, narrow, and elongated in character. Water collects in these troughs and their floors are often below sea level. The best-known example is the East African Rift Valley, which runs through Zambia, Malawi, Tanzania, Kenya, and Ethiopia, and extends along the Red Sea to Israel and Jordan over a total distance of 3,000 miles. It includes such lakes as Lakes Tanganyika, 4,700 feet deep, the world's deepest lake, Malawi Rudolph, Edward Albert, as well as the Dead Sea, 1,286 feet below mean sea level, the world's lowest lake, Fig, 67. Rift Valley Lakes, Fig 67. Earth movement 2. Lakes formed by glaciation, cirque lakes or tarns. A glacier on its way down the valley leaves behind circular hollows in the heads of the valleys up in the mountains. Such hollows are the armchair-shaped cirques or corries. Their over-deepened floors may be filled with water to become cirque lakes, e.g. Red Tarn in the English Lake District, Fig. 68. Those that occupy glacial troughs are long and deep and are termed ribbon lakes, e.g. Lake Ullswater. B. Kettle lakes. These are depressions in the Blee Water in Westmoreland, England. A typical Corrie Lake, J.K. St. Joseph outwash plain left by the melting of masses of stagnant ice. They are irregular because of the uneven morainic surface and are never at any great size or depth, e.g. the Meres of Shropshire in England and the Kettle Lakes of Orkney in Scotland. C. Rock Hollow lakes. These are formed by ice scouring when valley glaciers or ice sheets scoop out hollows on the surface. Such lakes of glacial origin are abundant in Finland. Indeed, the Finns call their country Suomi, the land of lakes. It is said that there are over 35,000 glacial lakes in Finland. D. Lakes due to morainic damming of valleys. Valley glaciers often deposit morainic debris across a valley so that lakes are formed when water accumulates behind the barrier. Both lateral and terminal moraines are capable of damming valleys, e.g., Lake Windermere of the Lake District, England. Downloaded from Shashid Thacker 23. Blog. Com67e. Lakes due to the deposition of G-Acir in glaciated lowlands with a predominant *run landscape where drainage is poor. There are invening depressions. These depressions are waterlogged, forming small lakes like Toast County down in Northern Ireland. 3. Lakes formed by volcanic activity, crater and caldera lakes. During a volcanic explosion, the top of the cone may be blown all, leaving behind a natural hollow called a CW. This may be enlarged by subsidence into a caldera. These depressions are normally dry, bounded by steep clill titikes, and roughly circular in shape. In dormant or extinct volcanoes, rain falls straight into the crater or caldera, which has no superficial outlet, and forms a crater or caldera lake. The outstanding ones are the Crater Lake in Oregon, USA, which in fact occupies a caldera, Lake Toba in northern Sumatra, and Lake Avemus near Naples, Fig. 69. Crater Lake Fig. 69. Volcanic activity, B. Lava-blocked lakes. In volcanic regions, a stream of lava may flow across a valley, become solidified, and thus dam the river, forming a lake, e.g. A lava flow blocks the Jordan Valley, forming the Sea of Galilee, which is an inland lake, rather elongated in shape. C. Lakes due to subsidence of a volcanic land surface. The crust of a hollow lava flow may collapse. The subsidence leaves behind a wide and shallow depression in which a lake may form, e.g., Mývatn of Iceland. 4. Lakes formed by erosion, karst lakes. The solvent action of rain water on limestone carves out solution hollows. When these become clogged with debris, lakes may form in them. The collapse of limestone roofs of underground caverns may result in the exposure of long, narrow lakes that were once underground, e.g. the Lac de Chalexin in the Jura Mountains. The large depressions called polges, which normally Fig. 70, a karst lake formed above the groundwater table in a limestone region, do not have surface outlets, may contain lakes. During wet periods, these may cover most of the polge floor, but they shrink during dry periods due to seepage, Fig. 70. An example is Lake Scutari in Yugoslavia. Solution is important in other rocks such as rock salt. Local subsidence may occur when the underlying beds of rock salt are gradually removed in solution. Many of the meres of Cheshire, England, were probably caused by this and are also the result of salt mining operations. B. Wind-deflated lakes. The deflating action of winds in deserts creates hollows. These may reach groundwater, which seeps out, forming small, shallow lakes. Excessive evaporation causes these to become salt lakes and playas. These are found in the Qattara Depression in Egypt and the Great Basin of Utah, USA. 5. Lakes formed by deposition, lakes due to river deposits. A river may shorten its course during a flood by cutting across its meandering loops, leaving behind a horseshoe-shaped channel as an oxbow lake, e.g. those that occur on the floodplains of lower Mississippi, USA, and Rio Grande, Mexico. B. Lakes due to marine deposits. The action of winds and waves may isolate lagoons along coasts by building spits or bars. As these lagoons of shallow water are enclosed only by a narrow spit of land, comprising mud, sand, and shingle, they may drain away at low tide. They are commonly found off the deltas of large rivers such as the Nile and the Ganges. In East Germany and Poland, lagoons are called hafels. Strong onshore winds are capable of pushing 68 coastal sand dunes landwards, and these may enclose marshy lagoons. This type of lagoon is well developed in the lands of southwest France. C. Lakes due to landslides, screes, and avalanches. Lakes formed by these processes are also known as barrier lakes. Landslides or screes may block valleys so that rivers are dammed. Such lakes are short-lived, because the loose fragments that pile across the valleys will soon give way under the pressure of water. When they suddenly give way, the dammed water rushes down, causing floods. Examples of lakes of this type are Lake Gormire in Yorkshire, blocked by landslides; F. Finnan Free on Snowdon, blocked by screes; Fig. 71. Fig. 71 deposition, a barrier lake formed by the deposition of an obstacle. Fig. 72 human activities, a lake made by constructing a concrete dam across a river valley. 6. Lakes formed by human and biological activities. A. Man-made lakes. Besides the natural lakes, man has now created artificial lakes by erecting a concrete dam across a river valley so that the river water can be kept back to Iorm reservoirs. Fig. Amongst such man-made lakes, the most imposing is Lake Mead above the Hoover Dam on the C. Colorado River, USA. B. Lakes made by animals. Animals like /black square are particularly interesting. They live in communities and construct dams across the rivers with timber. Such beaver dams are quite permanent and are found in North America, e.g., Beaver Lake in Yellowstone National Park, USA. C. Other types of lakes. These include ornamental lakes, especially made to attract tourists, e.g., Lake Gardens, Kuala Lumpur. Taping lakes. Man's mining activities, e.g. tin mining in West Malaysia, have created numerous lakes. Inland fish culture has necessitated the creation of many fishing lakes. Lakes and man, a careful examination of the lakes of the world will reveal their immense human significance. In countries where they are found in abundance, such as Finland, Canada, USA, Sweden and the East African states, lakes, together with other inland waterways, have played a dominant role in the human, economic, social and cultural life of the people. The pattern of settlement, commerce and communication is very closely related to the distribution of the water leeches. The following are the major uses of lakes and their associated human activities. 1. Means of communication. Large lakes like the Great Lakes of North America provide a cheap and convenient form of transport for heavy and bulky goods such as coal, iron, machinery, grains, and timber. The Great Lakes St. Lawrence waterways penetrate more than 1,700 miles into the interior. They are thus used as the chief arteries of commerce. It is estimated that the annual tonnage passing through the Sault Ste. Marie Canal, or the Sioux Canal, between Lake Huron and Lake Superior is greater than the combined annual tonnage of the Suez and Panama Canals. 2. Economic and industrial development. Early CTTC ments and town sites were very much influenced by the presence of lakes. Lakes are an even more decisive factor when they are drained by large rivers with outlets to the sea. The Great Lakes St. Lawrence waterways were responsible for the development of the interior wheat farms and lakeside industries. Raw materials, minerals and fuels were economically handled and assembled in the Holmes District, Lakes/Huron, Ontario, Michigan, Erie and Superior, which has since become one of the greatest industrial districts of the world. Similarly, Lakes Poyang, Tung Ting and other lakes at the central, some of the lakes of Finland scoured out by Ice Action Camera Press Yangtze Basin have greatly assisted in the commercial and industrial development of Wuhan, FFW Chang, Hanyang and Hankou. 3. Water storage. Lakes of either natural or artificial origin are vital sources of domestic water supply to surrounding towns and industrial cities. For example, in Britain, Lake Thirlmere supplies water to Manchester, Loch Katrine to Glasgow, Lake Vyrnwy in Wales to Liverpool. The Ochla Reservoir supplies Delhi, and the Vetana, Vihar and Tulsi lakes supply Bombay. 4. Hydroelectric power generation. In mountainous districts, lakes or man-made reservoirs are used to furnish a good head of water to generate hydroelectric power. Natural lakes are preferred to artificial reservoirs because the volume of water that flows from them varies very little throughout the year. For instance, the Niagara River flowing from Lake Erie to Lake Ontario has a very regular supply of water for its power stations, whereas the Catawba River in the Carolinas, which does not flow from a lake, has very little water during the dry season. Cotton mills have been forced to close down during the period of drought due to insufficient power supplies to run the mills. The Aswan Dam on the Nile in Egypt and the Lloyd Barrage on the Indus at Succa suffer from similar defects. The Abu Bakr Dam of the Cameron Highlands supplies much hydroelectricity for central West Malaysia. 5. Agricultural purposes. As mentioned earlier, most lakes will eventually be eliminated, and when they dry up, their former beds are covered with thick layers of fertile alluvium. They make excellent agricultural land like the fertile Vale of Pickering in Yorkshire, or the rich Red River Valley of Canada, which was in fact the former site of Lake Agassiz. Modern multi-purpose dams, besides generating hydroelectric power, also supply water for irrigation, e.g. the Sennar Dam on the Blue Nile in Sudan, the Burrinjuk Dam on the Murrumbidgee in Australia, and the Hirakud Dam, Madhya Pradesh, on the Mahanadi in India. 6. Regulating river flows. A river with large lakes in its basin seldom experiences serious floods or lack of water. By absorbing the excess water during heavy rain, a lake reduces the effects of serious flooding downstream. In the dry season, it releases its water so that a steady flow of the river is maintained. Because lakes retain part of the sediment load, rivers leaving lakes have clearer water. Lakes that have such functions include the Poyang and Tung El Ing on the Yang Tzed Kiang, Tonle Sap on a tributary of the Mekong, and Lake Constance on the Upper Rhine. Where such lakes are not available and flooding is a serious problem, artificial reservoirs are constructed, e.g. the Hoover Dam on the River Colorado and the Bakra and Nangal dams on the Sutlej in India. 7. Moderation of climate. Large and deep lakes, which are heated more slowly than the land by day and cooled more slowly than the land by night, exercise an appreciable effect in moderating the climate of a region in the same way as oceans affect adjoining land masses. Water in the lakes cools the air in summer by absorbing part of the heat and warms it in winter by releasing the heat. For example, the eastern shores of Lakes Erie, Ontario, and Huron have a much milder winter than those of the west because the oncoming breezes are warmed and early frosts are minimized. This part of the Lake Peninsula is therefore important for grapes and fruit farming. Large lakes like Lake Michigan and the Caspian Sea also exert a slight influence on the cloudiness and precipitation of the region. Their large expanse all-water acts almost like part of the ocean and helps to precipitate atmospheric moisture into rain. I.e. leeward side of Lake Michigan records a little more precipitation than the windward side, though the actual amount is often not easily noticeable. Small lakes have practically no effect at all on either temperature or rainfall. 8. Source of food. Many large lakes have important supplies of protein food in the form of freshwater 70 fish. Sturgeon is commercially caught in the Caspian Sea, salmon and sea trout in the Great Lakes, and in Tonic Sap in Cambodia, fishing is a leading occupation. Amateur fishermen have found fishing in lakes and rivers a most rewarding pastime. In many countries, artificial lakes have been created for inland fish breeding. This is particularly important in China and Japan. 9. Source of minerals. Salt lakes provide valuable rock salts. In the Dead Sea, the highly saline water is being evaporated and produces common salt, almost indispensable for human well-being. Borax is mined in the salt lakes of the Mojave Desert. Gypsum is mined in Cheshire, and Starsfurt, a small distance from Berlin, is so rich in potash and other chemical deposits that they have given rise to a wide range of chemical industrials. In both these areas, the salts are obtained from deposits formed in an earlier geological period. 10. Tourist attraction and health resorts. Some of the world's best frequented holiday and health resorts are located on lakesides, for example. Lake Geneva, Lake Lucerne, Lake Lugano, Lake Como, Lake Placid, New York, Lake Vänern and Lake Vättern, Sweden, the English Lake District and Taping Lakes. The glacier-formed lakes of the Alps have made the tourist industry a national occupation of the Swiss. Chapter 10 Coastal landforms. The action of waves, tides and currents. The coastline, under the constant action OCW/OS, tides and currents, is undergoing changes day to day. On calm days, when winds arc slight, waves do little damage to the shoreline and may instead help to build up beaches and other depositionary features. It is in storms that the ravages of the waves reach their greatest magnitude. One average PKUC of Atlantic waves on adjacent coasts is about 6 HLB per square foot in the summer, and treble that in winter during storms the pressure exerted is more than 0.100 lb, or 3 tons per square foot. Movements of such intensity will wear down not only the eliphals, but also sea walls and buildings. Waves and currents, on contact with the shores, make very little direct attack on the coastline. Rides affect marine erosion mainly by extending a line of erosion into a slash. One of erosion. Phi/1 corresponds to the area between the low water level and the high water level. 6 currents help to move eroded debris and deposit it as silt, sand, and gravel along the coasts. Wind turbulences. Fig. 73. The mechanism of wave motion, the mechanism of marine erosion. The most powerful agents of marine erosion are WOs. Their origin is due to the sweeping of winds over the water surface, which sets a series of undulating swells surging forward. These become higher and swifter. A normal wave in an open ocean may measure 20 feet high, the vertical height between the crest and the trough, and 400 feet long, the wavelength or the horizontal distance between one crest and another. During storms, this is greatly increased, depending on the speed and duration of the winds. On approaching shallow water near the shores, their speed is reduced, and the waves are curved or refracted against the alignment of the coast. Shallow water, when it is less than the height of the waves, checks their forward movement. The crests curl over and break into the shores in a mass of foam as breakers. The water that finally rushes up the beach and hurls rock debris against the land is termed swash. The water is sucked back and retreats as backwash. Another element in offshore drill is the undertow, which flows near the bottom away from the shore. This current exerts a pulling effluent which can be dangerous to sea bathers. Fig. 73. Marine agents of erosion operate in the following ways to transform the coastal landscape. 1. Corrosion. Waves armed with rock debris of all sizes and shapes charge against the base of the cliffs and wear them back by corrosion. Oncoming currents and tides complete the work by sweeping the eroded material into the sea. 2. Attrition. The constantly moving waves that transport beach materials such as boulders, pebbles, shingle, and fine sand also hurl these fragments against one another until they are broken down by attrition into very small pieces. The grinding and polishing of such fragmental materials against eliphal faces and against each other is largely responsible for the fine sand which forms the beaches that are so typical of the seaside resorts. 3. Hydraulic action. In their forward surge, waves splashing against the coast may enter joints and crevices in the rocks. The air imprisoned inside immediately compressed. When the waves retreat, the compressed air expands with explosive violence. Such action repeated again and again soon enlarge the cracks and rock fragments are prized apart. 4. Solvent action. On limestone coasts, the Sol *1 action of seawater on calcium carbonate sets at chemical changes in the rocks and disintegration tar place. This process is limited to limestone coasts. The rate of marine erosion depends on the nature of the rocks, the amount of rock exposed to the sea, the effects of tides and currents, and human interference in coast protection. Other effects such as volcanicity, glaciation, earth movement, and organic accumulations have also to be considered. Coastal features of erosion 1. Capes and bays. On exposed coasts, the continual action of waves on rocks of varying resistance causes the coastline to be eroded irregularly. This is particularly pronounced where hard rocks, e.g. granites and limestones, occur in alternate bands with softer rocks e.g. sand and clay. The softer rocks are worn back into inlets, coves or bays, and the harder ones persist as headlands, promontories or capes. Fig. 74. Along the Dorset coast of southern England, Swanage Bay and Durlston Head are examples. Even where the coast is of one rock type, irregularities will be caused by variation within the Fig. 74 coastal features of differential erosion rock. Thus, Penang Island, made of granite, has many bays and headlands. Very large indentations, such as the Persian Gulf or the Bay of Bengal, are due to other causes such as submergence or earth movement. 2. Cliffs and wave-cut platforms. Generally, any very steep rock face adjoining the coast forms, the rate of recession will depend on its geological structure, that is, the stratification and jointing of the rocks and their resistance to wave attack. If the beds dip seawards, large blocks of rock will be dislodged and fall into the sea. The elliptical will rise in a series of steps as shown in Fig. 75. On the contrary, if the beds dip landwards as illustrated in Fig. 76, the elliptical will be more resistant to wave erosion. Some Fig. 75 cliff beds dipping seawards. Fig. 76 cliff beds dipping landwards of the best-known cliffs are the chalk cliffs of the English Channel and include Beaky Head, which is 500 feet high, the Seven Sisters near the mouth of the Cuckmere, and the White Cliffs, Old Dover. At the base of the cliff, the sea cuts a notch, which gradually undermines the cliff so that it collapses. Zone of initial land. Fig. 77, the development of shore profile downloaded from Shashid Thacker 23. Blog. As a cliff recedes landwards under the pounding waves, an eroded base is left behind, called a cut platform. The platform, the upper part of which is exposed at low tide, slopes gently seawards on a surface, is strewn with rock debris, elrom the Risser U cliff. Further abrasion continues until the pebbles are swept away into the sea. The eroded materials are deposited on the offshore terrace. Fig. Black square when the platform attains a greater width, e.g. 30 miles in the case of the War/E-cut platform at Strand Flat off western Norway. It is entirely covered with water and further erosion of the cliffs is negligible. 3. Cave, arch, stack and stump. Prolonged wave attack on the base of a cliff T excavates holes in regions of local weakness called caves, e.g. at Flamborough Head, England. When two caves approach one another from either side of a headland and unite, they form an arch, e.g. the Neddy Eye near // Scotland. Further erosion by waves will ultimately lead to the total collapse of the arch. The seaward portion of the headland will remain as a pillar of rock known as a stack. One of the finest examples of a stack is the Old Man of Hoy in the Orkneys, which is of old red sandstone and is 450 feet high. Equally out Fig. 78 arch, stacks and stumps. Where two caves are eroded on either side of a headland, they may eventually join to form a natural arch. If the top of the arch collapses, stacks are formed. These are gradually worn down until they become stumps exposed only at low tide. Standing are the Needles, Isle of Wight, which are a group of stacks cut in chalk and diminishing in size seawards. In the course of time, these stubborn stacks will gradually be removed. The vertical rock pillars are eroded, leaving behind only the stumps which are only just visible above the sea level, e.g. those of the St Kilda group, oil the Outer Hebrides, Scotland, Fig. 78. 4. Geos and gloops. The occasional splashing of the waves against the roof of a cave may enlarge the wave-cut platform on the Hong Kong coast. Fock joints when compressed air is trapped inside. A natural shaft is thus formed, which may eventually pierce through to the surface. Waves breaking into the cave may force water or spray or just air out of this hole. Such a shaft is termed a gloop from the noise made by the water gurgling inside, or blowhole, Fig. 79. An example is at Holborn Head in Caith Cliff top through which air or Fig. 79 gloop water are forced. Ness, Scotland. The enlargement of blowholes and the continued action of waves weakens the cave roof. When the roof collapses, a long, narrow inlet or creek develops. Such deep clefts, which may be 100 feet deep and equally long, are called geos, e.g. the Wife Geo, near Duncansby Head. Scotland, Fig. 80, Fig. 80 geo-coastal features of deposition 1. Beaches, sands and gravels loosened from the land are moved by waves to be deposited along the shore as beaches. This is the most dominant form of the constructive work of the sea. The eroded material is transported along the shore in several distinct ways. The longshore drift, which comes obliquely to the coast, carries the material along the shore in the direction of the dominant wind, Fig. 81. At the same time, the backwash removes pan of the material seawards along the bed of the sea and deposits it on the offshore terrace and even beyond. Finer materials such as silt and mud are deposited in the shallow waters of a sheltered coast. The constant action of the waxes automatically sorts out the shoreline deposits in a graded manner. The coarser materials, cobbles and boulders, are dropped by the waves at the top of the beach. The finer materials, pebbles and sand grains, which are carried down the beach by the backwash, are dropped closer to the sea. On smooth lowlands, beaches may continue for miles, like those of the east coast of West Malaysia, but in upland regions where the land descends abruptly into the sea, such as the Chilean coast, long beaches are absent. 2. Spits and bars. The debris eroded by waves is continually moved by longshore drift, and where there is an indentation in the coast, such as the mouth of a rixa or a bay, material may continue to be deposited across the inlet. As more materials, Fig. 82 development of spit are added, they will pile up into a ridge or embankment of shingle, forming a tongue or spit, with one end attached to the land and the other end projecting into the sea, Fig. 82, e.g. Calshot Spit, Southampton Water. England, or those along the coast, Kellenton. Oblique waves may curve the spit into a hook or recurved spit. When the ridge of shingle is formed across the mouth of a river or the entrance to a bay, it is called a bar. The most remarkable example of a bar is Chesil Beach in Dorset, England, which extends for over 16 miles along the coast, linking the Isle of Portland with mainland and enclosing a lagoon called the Fleet. Such a connecting bar that joins two land masses is better known as tombolo. On the Baltic coast of Poland and Germany, large bodies of water are almost completely enclosed by long bars, locally termed nerungs, to form marshy lagoons or half-titikes. 3. Marine dunes and dune belts. With the force of onshore winds, a large amount of coastal sand is driven landwards, forming extensive marine dunes that stretch into dune belts. Their advance inland may engulf farms, roads, and even entire villages. The dunes of the Landes, southwest France, cover 6,000 square miles. The crests of the dunes are over 130 feet high. Dunes are common in the coast lands of Belgium, Denmark, and the Netherlands. To arrest the migration of the dunes, sand-binding species of grass and shrubs, such as marram grass and pines, are planted. Types of coasts. Despite a great variety of coastal features, coastlines may be divided into two basic types. 1. Coastlines of submergence. These are due to the sinking of the land or the rise of the sea, including such coasts as rear coasts, fjord coasts, estuarine coasts, and Dalmatian or longitudinal coasts. 2. Coastlines of emergence. These are due to the uplift of the land or a fall in the sea level. They are less common and are represented by the uplifted lowland coast and the emergent upland coast. Coastlines of submergence. 1. Rear coasts. During the Ice Age, a great deal of water was locked up in ice. The warmer climate that followed melted much of the ice. Subsequently, there was an increase in the waters of the oceans, and the sea level rose appreciably. In some cases, it is estimated that there was a rise of almost 300 feet. In upland coastal regions where the mountains run at right angles to the sea, that is transverse or discordant to the coast, Fig. 83. A rise in the sea level submerges or drowns the lower parts of the valleys to form long, narrow branching inlets separated by narrow headlands. They differ from fjords in two important respects, i.e. they are not glaciated, and their depth increases seawards. A rear coast is typical the Atlantic type of coast like those of northwest France, northwest Spain, southwest Ireland, Devon and Cornwall. As rears are generally backed by highland, they support few large commercial ports, though they have deep water and offer sheltered anchorage. They have been extensively used for sighting fishing P-degrees RTS and naval bases such as Plymouth and Brest. 76.2. Fjord coasts. Fjords are submerged U-shaped glacial troughs. They mark the paths of glaciers that plunge down from the highlands. They have steep walls, often rising straight from the sea, with tributary branches joining the main inlet at right angles. Due to the greater intensity of ice erosion, fjords are deep for great distances inland, but there is a shallow section at the seaward end formed by a ridge of rock and called the threshold, Fig. 84. Of the fjord coast are Fig. 84 a fjord coast, submergent and glaciated, numerous islands or skerries which, with the shallow thresholds, sometimes only 200 feet deep, complicate coastal navigation. Fjord coasts are almost entirely confined to the higher latitudes of the temperate regions which were once glaciated, e.g. Norway, Alaska, British Columbia, southern Chile, and the South Island of New Zealand. Some of the large fjords are extremely long and deep. For example, the Sogne Fjord of Norway is 110 miles long, 4 miles wide, and almost 4,000 feet deep in its mid-channel. Despite their deep and sheltered water, two large ports are located in fjords. Their mountainous background with poor accessibility inland attract two settlements. Agriculture is confined to the E*alk fans built up where streams flow down to the fjords. The few towns that exist either as fishing or market centres, e.g. Trondheim, are only of local importance. 3. Dalmatian coast. This is the longitudinal coast where mountains run parallel or concoit to te coast. The name is taken irony the coast of Dalmatia, Yugoslavia, along the Adriatic Sea, where the subme gents of the coastline produces long, narrow inlets with a chain of islands parallel to the coast, i.e. Fig. 85 a Dalmatian coast, concordant Pacific type. Elongated islands are the crests of former ranges and the narrow sounds were the former longitudinal valleys. Fig. 85. The Dalmatian type of coast is also typical of the Pacific coast where the ranges are parallel to the coast, e.g. western coasts of North and South America, but there the coastline is more regular. Like the rear and fjord coasts, the mountainous nature of the Dalmatian coastline hinders communication inland. It has deep, sheltered harbors but no distinguished ports. On the Pacific coast, however, there are some important ports such as San Francisco. 4. Estuarine coasts. In submerged lowlands, the mouths of rivers are drowned so that funnel-shaped estuaries are formed. If their entrances are not silted by moving sandbanks, they make excellent sites for ports. E.g. the estuaries of the Thames, Elbe and Plate are the sites of such great seaports as London, Hamburg and Buenos Aires. Tidal effects further enhance the value of the ports, and even when there is a little silting, modern dredges help to keep the ports open all the time. Coastlines of emergence. 1. Uplifted lowland coast. The uplit part of the continental shelf produces a smooth, gently sloping coastal lowland, Fig. 86. The offshore waters are shallow with lagoons, salt marshes and mudflats. 77. Where the emergent deposits front the continent shelves are sand and gravelly, beaches muine dunes are formed. Ports that were once located on the former coast become inland towns. Examples CS of uplifted lowland coasts include the southeastern USA, western Finland, eastern Sweden, and parts all coastal Argentina south of the Rio de la Plata. Emergent upland coast. Faulting and earth movement may thrust up coastal plateau so that the whole region is raised, with consequent emergent features. A raised beach is the most prominent. The raised beach is beyond the reach of the waves, though it may still possess arches, stacks, and other coastal features. The emergent upland coast is quite straight with steep cliffs and deeper offal shore water, for the waves have not yet eroded lines of weakness or carved a wave-cut platform. Fig. 87. It has little potential for good port sites. Examples of emergent upland coasts are found in Scotland, the western coast of the Deccan, India, and the western Arabian coast facing the Red Sea. Fig. 86 lowland coastline of emergence.